Okay, so let's talk a little bit about some algorithms that, yes, we're going to talk about this in the guise of memory and memory management, but these are also things that you'll kind of see in different places all over in computer science. So definitely keep your eyes open and think about these in different places. Again, I'll talk about the good, the bad, the uglies, and some of these and how they work. But as we think about some of these, I kind of highlighted this optimal algorithm as an example. Sometimes we call it best fit or something around the fact that we've gone and we've understood everything and we found the perfect way to do it. Well, that's usually the most costly. So sometimes it's not the best one to use, but it depends on, is this a time-sensitive thing or not? Not recently used, which is an interesting one. If it's the most recently used, would you think that that would be the one that we would get rid of because it probably would be the one we're not going to use, or should we use the one that hasn't been used in the longest amount of time? So, and some of these like FIFOs are always kind of that, the introduction to thinking about what's fair. First in, first out, usually from a queuing perspective, only works if there's one, atomic thing that works there. So sometimes it does, sometimes it doesn't. We'll talk about second chance, which is kind of your way to say, okay, well, I know you're kind of low on the totem pole, but we're going to, give you a second chance and, see if you're the one to not be replaced. Clock algorithms are any form of round robin in a way that might be based on, some other thing which could be used somewhat in a random fashion. Could be something that, might be terrible to use if, the way you define your clock or your round robin, might artificially change itself to, always be trying to be, the same value. So let's say that your CPU cycle does something and it only ever gives you CPU when it's about 1 second or 10 or 11 seconds or 21, and you use that one. Well, that's going to be artificially kind of changing that. Least recently used, which is kind of in the not recently used. Talking about working sets, so getting a little more advanced in thinking of how we could do that, and then we'll kind of round out with the WS clock algorithm. So if we think of not recently used, and just think about that for a second, we're dealing with page faults, and page faults are really going to be something that happens because we thought something, or we were told something was in memory and it's not. And so what we need to do is we need to go get that, piece of data from disk, whether that's a binary executable piece or if it's just data or whatever it is. But we have to go get it. And so we got to think about, okay, when we go do this and we page fault, we have to look at these pages and then we have to figure out where we're going to put them. So in not recently used, it's an interesting way to think about, okay, well, if it's not the most recently used, if it's kind of, maybe not the least, but it's just one that's been, kind of sitting out there for a while, is the assumption that by doing that we're not going to page fault that again because now this is going to be the most recently used. So many ways to think about this and actually get it done, but you can kind of look at, looking at different algorithms to get this done. So this one really kind of looking at this idea of these R and M bits, and are they referenced and modified is what the R and M stand for. So you can kind of see the different classes here. So it's not referenced, not modified, all the way to reference modified. And with that, then we can kind of take that into, I thought I had another slide here, into how those classes are actually used. So by taking this algorithm and kind of plugging it in, what we're kind of trying to say is that we can mark all of these different pages, these segments of memory, let's say, and as we classify them, we can easily come down and say, okay, well, I want a class 0 or a class 2, whatever, and we can kind of use that as a very quick mechanism to figure it out. Now notice it says bits. This is because, again, we have to be able to find this stuff and make decisions in like time one, like not 10 times something or, order of n squared or anything like that. That would just take too long. So these are just modes of, how we could leverage bits to represent, things that we could ask easy questions of. This is second chance, and it's kind of that idea that the A here is the least recently used. It's the last one. And so its second chance is that it goes actually to the top. So instead of it just getting knocked out right away, assuming this is all available memory, and this is kind of, H is the newest, G, and you can see H, G, F, these kind of correlate this way. A really kind of comes in and says, okay, let's put you back to the front. Now, why would you do this? Is it assumed that the one that's least recently used is probably going to be the one that's used anyways? So let's just pull it up there. So is this least recently used and then not? We'll see that the least recently used in a second, but that's just kind of the whole idea around second chance. The clock page replacement is just one that really kind of takes this either round robin approach or something around, thinking about, okay, a random victim, let's say, that we're going to get rid of or we're going to use to pull in, just gets chosen, somewhat at random. And so looking at how this would kind of render itself through, thinking about, a clock is an independent thing that kind of moves the hands around, but you can easily think about this more as a round robin, just with a different pointer, different mechanism to get there. So here's least recently used, and again, we're looking at these pages, and we're kind of going and we're putting in these bits, right? So you can see how these bits kind of flow up. So you've got, 1 is that one, 0, and then you got a 1, 0, and 1, 1. So that's oddly kind of tipping it on a side and representing, this at this specific time, what happened. And then as you see the clock tick and kind of move through, you can kind of see how things change. So, kind of following this all the way through, this only dealt with this bit. This one deals with the 2 front bits, then 3, then 4, then 5, and so on and so forth. So, following that through, you can kind of look at, who would be the victim in page faults. Segmentation. Yeah, so as we think about memory and we think about the use of memory, and we know that, bits and bytes and, maybe even little bigger variables, but, we have gigs and gigs of memory. And how we use them and how we actually allocate it can't be at a bit level. It just takes too long. We'll learn when we get to file systems, it's the same problem with character-based versus block storage. If we had to read and write files a character at a time, computers would still be almost too slow to use. So we have to find faster ways to do it, and some of that is creating different blocks, and some of it is actually just dealing with segmentation. So when we think about this and kind of segmentation, we can think about segmentation of blocks or chunks of data or chunks of memory that we can use. But then it's also important to think about, okay, well, what about the things we're actually storing in there? And do they have defined boundaries? Do they have things that are specifically set up for, a format? And so we do know that things like binary executables are in a very specific format. If you were to go out to any version of a Linux OS, anything like that, and if you were to go, make this a little bigger here. Okay, so get my cursor back here. So if we go look in, let's just say the bin directory, there's executables in here. And there's a command called file that will tell you what kind of file it is. And it's not perfect, but it kind of can look at it and it knows based on its format. So this one here is a Mako 64-bit executable. Here's another one that is actually 64-bit executable as well as 32-bit executable. So the point isn't necessarily what these are, but I see all these as executable. If I go into this directory and I look at what's there, it's just a bunch of ASCII text and directories and some other things. But the reality is that we do know that from a segmentation example, we can format certain things in certain ways, and we know where certain things are. And then when we look at this logical kind of stacked view, we can look at things like, the source text, we can look at symbols, we can look at all kinds of different pieces. So as we think about dealing with that and thinking about segmentation, we're going to talk about that more when we get into more virtualized memory, as well as some of the stuff we'll do in file systems. So working set. So this is again taking the algorithm a little bit further than just simple bits and identifying very quickly where something's at, because there isn't a lot of necessarily power in that. And one thing that we kind of look at all the time is what happens over time, and what happens when everything needs to be computed at once. What happens? Do we get to a point that the system is kind of falling down a cliff and can't recover, and what can we do about that? And that's kind of what this is representing, is what would happen as we kind of push that out over time. Looking at this specifically in its stack reference is again going down and looking at a bit in somewhere, but there's more information that actually goes with this. So you notice on the left-hand side, it's information about the page, the last time of use, and all these other things. And so as you kind of look up, quote unquote, what is your working set, which is going to be shown, kind of more on the right of the bits that are, kind of referenced or not referenced. You can kind of look here and say, okay, the algorithm is if R is 1, set the last time and the current time, so now we know that it's being used. If R is 0 and age is greater than whatever time you want to give it, get rid of it. So that way you can kind of remove it. Now, rare is it that somebody would actually do this exact step, because we don't really want code out there necessarily combing and cleaning and guessing. But if it's part of the algorithm and it makes this request, it might be it's removing it or replacing it. So it depends kind of what you do. And if R is 0 and the age is less than, or equal to that time you give it, remember the smallest time. So just another algorithm, another way to kind of make this work. Now, if we put two of them together, a working set and the clock, then we think about, both of these put together. And this is really where, and when we talk about CPU scheduling and some of the ways to do that, it's a common thing as well, is usually you're mixing things together. And why do you do that? Because one by itself sometimes doesn't work well, and sometimes even if it does work well, it doesn't work, in the bad instances, where things are falling apart. So sometimes you just need a little bit of fail-safe. And so, as an example, in the Completely Fair Scheduler in Linux, there's actually 3 different levels. And so you might be in level 1, and hopefully if your job's small and you get out and you're done, great. If not, you fall to level 2 and you can fall to level 3, and there's just different priority on how those are used. And that's done because it makes it a calmer situation. If something's really trying to hog all the CPU, it will put it down in that 3rd level and kind of give it less of what it thinks it should be doing and leave the real-time stuff more at the top. So just this is an example of just putting these two together and kind of thinking about time of last use and the R bit, but only if it's selected. So just adding those two things together. So just an example of R equals 0, and it's not saying here what. So if R is 0, and it plugs in the new page. Okay, I was trying to find. Okay, and then update the time. Okay, so that's kind of from this to this. I'm just kind of plugging that through. Now you'll notice a couple things. So the hand moves to this one over here, as well as this one. It's not saying the time, that's what I was looking for, but assuming this is greater than the time, then this is going to be replaced. And so that's what I was talking about here in the algorithm. Sometimes it's not, it depends, we're not seeing that in this run, but that's where this one is remove this page, but it's really in this example replacing this page with a new one. So kind of looking through some of these. Now, we didn't go over some of them, like, let's see, which ones did we go over? So, FIFOs are pretty common to talk about, but they're, in practicality, they're too simple, I think. And it's at kind of that grocery store line. Just because you're in line and you've got 10,000 items in your cart, it's not fair to the guy behind you that has one that you have to wait. So, again, I'm using computer fare, not grocery store fare, but we'll see a lot of these, and I think we did talk a little bit about least recently used, but the not recently used is a crude approximation. Because does it really matter? Do you have to get as finite as finding the exact one, or is it just important to know that you got to grab one that is in the least recently used bucket? Because it's really not that important to find the most recent, least recently used. So, when we think about this whole page replacement thing, we have to think about, kind of in that segmentation mentality as well, how we want to look at, finding victims or finding frames that we can get rid of, and what's the most efficient mode to do that in. And if we think about, segmentation on local versus global, should you be in all of your CPU requests through all the things you could do in your single process, should you be in a pool with every other process, or would an algorithm make more sense to really just kind of look at your process by itself? Because if you just use memory, is that memory going to be used again? Or is that something that you probably know will never be used, so you can swap that in and out? So this is kind of that thought around how we could segment things down a little bit. And this, again, is pretty common as you look across many things, that it might not make sense to just go in a global pool, because you might create an algorithm that's actually worse than just picking random victims here and there based on how it performs. So just kind of looking at how that kind of pushes itself through. So here we've got page faults, and then we've got number of page frames assigned. So as you look here, what's kind of really being represented in this A and B is kind of the high and low watermark around where an algorithm could take you, depending on is this, I think it's A versus B. I think in these numbers here is what they were representing in different buckets, to show that there's a lot of page faults per second here versus B, kind of just not having as many. So again, as we break up data, we do know that as we get stuff allocated to us, we think about them in these kind of stacks, right? So in a virtual space, we want to think about always starting at 0 and going up to sometimes we put the max that you could ever have up here, or sometimes there's little arrows to kind of say there's stuff that could fit in the middle. But we think about how we use this stuff in different forms of segmented space. Now, keep in mind that each of these blocks in reality are probably all over the place. But when we think about it in a logical view or a virtual view, we have to think about it as kind of the stack and how do things render together. And that's why we have those MMUs to go look up the real address, based on kind of where we're at. And some of these might actually be contiguous, some are not, but we think about it this way. Now, in this single address space, is this something where you, as a process, are going out and asking the kernel for memory and saying, I need, all of this space, and I'm going to plug everything in there, and I'm going to, put maybe my program, my text, all the things, and my variables and everything in one section, and then the rest is going to be leveraged for the data I'm going to be using, my stack and heap? Or would I look at it differently as two different spaces? So, kind of looking at the program in the I space, and then, the data over here. Well, now we got all these unused spaces here, so it depends on how it's allocated, but, just two examples of kind of looking at that. We can also look at things that are not only per process, so out of the process table we can point at different programs, and then the programs independently would know I'm pointing at this process, but I'm also pointing at this data segment here. And then what this one is representing up here is a second process. So let's just say this is process 101 and this is process 506. What you see here is both of these are pointing at the same program. Now, the only way that this can happen is through a function called dup, D-U-P. And that duplicates a given process to function together. If this was showing one extra linkage out, this could be the example of having two different two different running programs, just maybe pointing at the fact that this is the executable program. But the point of this is really that there's two different data tables, or two different data segments, sorry, and how we can share the program because the program is read-only. It never changes. But the data that you use is completely independent here. An example of this would be printf. Anything in the standard I/O library. This is actually what's known as a shared object library. And the first thing that invokes printf throws it in memory, and it just stays there forever. Everybody can use it, everybody can point at it, but what you're doing is you're bringing your own buffers to the party, and that's how you can get rid of race conditions and all the other bad things that could happen, and that's an example of this. So if two people are calling printf at the same time, which isn't necessarily a program, but let's just say it's a function in there, they would be leveraging their own data that they would be pointing at out of the process table, which are independent, and they can't see each other. This isn't necessarily a shared library. It's more kind of showing shared memory. And there's a difference there in that shared libraries are things that are kind of running on behalf of the system. They're out there, and they're a segment of memory that is just used. So it could be something like this, but the difference is that you wouldn't have this space represented as this space. You would actually just have a pointer to that space. But what this is kind of showing is that both process 1 and process 2, again, printf could be an example here, would be something that we would go, call and run, and everything would be fine. Really what this more represents is shared memory, which is a completely different thing. It is an actual form of interprocess communication, IPC. And what you do with shared memory is you have to create it at kind of the system level, let's say. You create your shared memory, you allocate it, and really all it's doing is it's taking the permissions off of that segment of memory and basically saying, don't segfault if anybody uses it, but anybody can use it. So there's a lot of race conditions, a lot of other negative things that could come with it, but that's kind of more what this would represent. Okay, so how do we deal with these page defaults and what really happens behind the scenes? So we think about, something physically has to happen. So a hardware trap, goes to the kernel, and that kind of, starts off this whole process of saying, okay, let's stop. So this is kind of the example that if you're in the grocery store line and everybody could only check out 10 things, this would be at the 10th thing, a hardware trap goes off and says, okay, hold on. Let's save everything. So let's print out your receipt, and let's take all of the stuff that's already done, put it aside, and then, basically go to, so step 2 would be dealing with that. Then it kind of goes into 3, which would be kind of that idea, okay, well, why don't you go get back in line? Why don't we know that, we need some more resource, we need to go get something. And then once we know that everything has kind of happened, number 4, then we're going to go really kind of look at that, and this is where algorithms start to kick in of, finding, what's needed, finding where to put it. Again, if we're in a virtual space, we're kind of thinking about, okay, how do we either fix the fact that we said we had something that we don't have, or we just never pulled it in the first place. So, and this is kind of in the midst of the mid-process running. So then we have to think about, okay, now we know this, and so is this something that we're going to pull in from disk, and then we kind of, think about, taking the physical frame and filling it in and then mapping it again to that virtual space. But, number 6 comes in and it says, okay, I'm going to go pull this stuff off disk, bring it into memory, do all the mapping, and then kind of come back to number 7 where, we have to then have different interrupts that happen because I/O has to go through and read something off of disk, put it in memory, and keep in mind that it's one of those critical things in all of computing that nobody talks about, but the speed of I/O, the speed of RAM, the speed of anything are all so different that we have to kind of have these mechanisms to say, the flag's on, I'm doing something, don't touch me yet, or I'll let you know when I'm done. because you can't pull, you can't sit there and ask all the time. So really, there's a second whole thing going on when you actually have to go to disk and pull that off, where it's going to be an I/O interrupt or I/O mechanism that says, hey, when I'm done, then you can know that everything we have is in memory and you're good to go. So then we get back to the point of the whatever caused the page fault. Let's just say that it was a missing piece of code that never got pulled in. It was lazily loaded, they call it. So when that gets back to its state, that's kind of that idea that, okay, well, let's go put everything back together. Let's put you back in line. Let's get you back to the register. Let's get everything kind of running again. And then, kind of start from where that ended up. Now, you can see in all these steps that there's a lot of stuff going on, right? I mean, it's stopping registers, copying registers, moving them somewhere, doing I/O, doing this and that. So are page faults expensive? Yes. Are they something that we could avoid? Not really. Could we make a system that never does that? Yes, but it would be a very, very minimalistic function, like an embedded system or something that really only had kind of one or two functions to use, because you would have to plug everything that thing would ever use into memory and never touch it and make it kind of almost read-only. So it's something we need to deal with, but that's why it's important to understand these algorithms and think about, from a fundamental perspective, what if I chose an algorithm that's just not as optimal as kind of what's here? What would happen? Now, there's two ways to think about disk, and I think these get a little confused back and forth, but there's the idea of executable code. And so, like in that, when I showed you the bin directory, bin ls is executable code. And so when I think about what we just talked about, page faults and pulling stuff off a disk, that's what I'm going after, is the actual text or the data or whatever, of a piece of code that's on disk that I have to put into memory. So I take that, I put it in memory, I'm good. The second thing is what's called swap, and swap space. Swap is actually a mechanism that's used for when you run out of RAM. So let's say you run out of RAM and there's really nothing to do. If you don't have somewhere to offload some of that stuff, then you're just going to pick random victims, and probably over time, depending on what's going on with your system, you could beat it up to the point that it just doesn't work anymore. So the idea is, why don't we take the things that are not used that much, or the victims we chose, and instead of destroying them, we just put them back on disk in a defined part of the hard drive that is non-viewable by humans. So it is a file system. We'll talk about it more when we get into file systems, but it's a file system that is defined, that has its own type of file system. We can't CD into it. We can't mount it. We can't look at it. And it's the place where, when things get swapped out, maybe you're going to use them again, maybe not. So maybe you swap them back in, but it's usually a space that, I don't know, I've always kind of remembered the rule of thumb back years ago that it was 2 times the amount of RAM plus 1 meg. So yes, you have the ability to go put all stuff back there, and yes, you can pull it back and forth, but it's really kind of that place to go to when you run out of RAM. One other thing about swap that's kind of an interesting one is, some people I kind of talk to here and there, and that have built a lot of stuff around, very high-end systems and how they run like that. We've discussed a lot, well, why not just not have swap? Is it really needed, or should you optimize? And so there are certain systems that are out there in the world that just don't use swap. So it's not it has to be their kind of thing. It's more of a, for general computing uses, it's there for memory management. So now we kind of step back and we think more about memory management as a whole, and we think about this MMU thing that is more of a hardware thing between the CPU and even its registers and memory, and its ability to be extremely fast of mapping virtual to physical memory. We've got the page fault handler, which is a completely different subsystem thing that knows, okay, when I went to get that data, that I said was there, and it's not there. And it's not there because we didn't pull it in or it got swapped out. We're going to have to go get it, and there's all this other stuff that has to happen. It might use the MMU to map some stuff, but it's a completely separate thing. And then we've got other things like an external pager running in our space and where we can see actually dealing with some of the memory management. So there's different pieces, and there's many other pieces that kind of go to this, but you need to kind of think about the whole thing that happens, as we looked at those 10 instructions earlier, on when a page fault happens or when we're needing to go access memory, what that really means and where it goes. So here's just an example of kind of where some of these fit. And again, you've got your kernel space and your user space, and again, we can't see the kernel space, but we know that there's an MMU in there, and sometimes I think it's usually always hardware. And then we've got the fault handler, but then you've got this external pager, and this is the thing that actually goes and does the I/O with disk. So this could be the thing that says, ooh, yeah, I need to go get this thing off, bring it back in, and a user process is independent of that. This is just something else that's running. The user process could cause the page fault, obviously, that would kind of make all this stuff happen. So if you follow it through here, so page fault happens, and it's basically telling the kernel that. So the program itself, you don't write code and say, oh, well, I'm going to, when I cause a page fault, this just happens as part of the, execution of the process. But once that happens, then this demand goes out in need. You actually go get it off a disk. You pull it back, mark that it's, handled. Everything's good to go. You map it, and then you send something back to the user process to start up again. So I think my slides got mixed around here a little bit. We started to talk about segmentation. We're going to get back to it here. So as I was saying, as we look to segment data, there's many different ways to think about it. We'll talk about blocks and chunks and slabs and all that stuff later. But this is really just thinking more about the fact that we need to segment certain kinds of data certain ways. Now, what's interesting about this, as let's say this is a running process. Your source text will never change. Your constant table, which is variables that have a defined size, which in C code everything is a defined size. Your variables, you can't add or delete variables as you're flying, but what they actually house might be different, but they're still going to be of constant size. So the value in it might be different. The size of an int is always going to be the size of an int. The size of a char is going to be a char. What's in there, it necessarily doesn't matter. Most people get lost on pointers, and they think, well, pointers are dynamic memory that can grow and shrink. No, pointers are at a defined size. They're exactly the size of your OS and your architecture. So if you're a 64-bit, that's how big a pointer is, and it just points at memory. So as the pointer points at memory, we know that that is maybe pointing at a bit, a byte, a gig of data. You don't know, but the reality is what you're pointing at is not part of your code. That's somewhere else in different. Well, I guess it depends on what it is. If it's something you created using malloc, it's going to be up here in your stack. If it's something that you're pointing at that's shared or something else, it will be outside of your stack. So if we know that there's certain things that are going to be exactly a certain size, we can either build them in segments and chunks. We can break them apart and know that, well, this nice easy stack here really is just kind of broken apart into these different segments, and we just need to point to one another and know where that goes. But really, if you fundamentally get all the way down deep into a computer and you think about, okay, well, what am I really doing? You're taking data off disk, you're putting it in memory. Memory gets pulled into registers. The registers are the only thing that the CPU can talk to. And the registers actually manage the computation of something and then it going back into memory. And then once that thing's back in memory, think about this. There's got to be all those buffers and all those caches and all those triggers and I/O handlers and, all the other things that happen. And as all of that is kind of flowing back and forth, really all you're doing is just kind of pointing in different memory segments. So where these are and how you want to think about them are completely up to how the OS is designed. We don't necessarily need to know or care how big they are and where they sit, but just to know that they're, chunked in a certain way. So if we think about the difference between, paging versus segmentation, knowing that, in paging, a programmer doesn't need to know anything about that. It's just inherent. It happens in the system. It's a kernel level call. It's not something you compile in your code or you manage or you do anything with. But in segmentation, you do. So you have to know where all that is because you have to know how to point to it. Linear address spaces, well, there's just one in paging because it's your space. It's your virtual memory that starts at 0 and moves to whatever. But in segmentation, you can't have many. Now, the total address space going beyond physical memory is not paging and segmentation as much as it is just that whole virtual memory concept. So, of course, both of them can do that because they're a virtual thing, not because they're a page or a segment. Can procedures and data be distinguished and separately protected? Well, obviously in paging, no, because there's only one, so you can't separate. But that's the whole point of segmentation. Tables whose size fluctuates accommodate easily. Well, with paging, no, because you can draw the stack and the heap, but the reality is those are just kind of a virtual way to represent it. But in segmentation, that's actually the point of having all those things separate. Sharing of procedures between users. In paging, no, because you're in one segment or one piece of code. Where in segmentation, that could be the things where you're just pointing at different things. So different users can all kind of use that however they want. So we think about, the difference in, why we use both of these was, paging was created to create virtual memory, really. And then segmentation is really kind of that, more of the concept of, allowing other people to access things that, if they're read-only executable components of code, there's no point in everybody having the same thing running around. So why don't we just point to each other instead of, trying to deal with, bringing all that with us? Because how silly is it that all of us have printf in our code, and every time we go to execute it, it's the exact same instruction, the exact same code, but then we're fighting for memory segments or fighting for memory space because somebody else used it once and then they were least recently used, so they got kicked out, and then I used it. So segmentation is just a way to kind of expand upon that. Now, this is where we can talk a lot about what these look like and all this, but what I'll talk about is a little different because in any form of breaking something down into blocks or chunks, especially when they're dynamic size, becomes very dangerous. And it's dangerous for a couple of reasons. All of it does lend itself down into what's called fragmentation. So I will have internal or external fragmentation. Internal is easy, and that one kind of is something you can follow through, because if I have a 7K segment here and I'm using 1 byte, then the rest is lost. That's internal. External is a space between. Now, if you see here D, this is the worst case, right? I got all these little, a 3 and a 4 and a 3K, but what if somebody comes in and needs 5? I have 5 in total, but I don't here. So I need to kind of defrag it. This is what we used to actually do with hard drives. And so now I have this nice, easy, clean, big chunk there that I can use. So Multics is an actual OS that was, I don't know if it was written by I think Minix was written by the author of this book, but Multics is just, another form of an operating system. And the idea that they had was, if you look at segments, and they use 36 bits to describe or, to have that segment descriptor. So you can easily kind of figure out in a 32-bit OS, this would fit in there. And really has pointers to other page tables. So this way you're chunking things down, but again, this gets back to that whole idea of it's easier to do a search in like encyclopedias or to go through, something based on, maybe the first couple bits of something to point at the second one versus trying to linearly go through one big table. So this would be the example, and I think this is the 36, right? So I got 18, 6, 28, 30. Yeah, so this is your 36. So you notice this is the actual memory address. So you only got 18 here, but then you have to define which segment length it is, and then you're seeing some things here. So is this 1024 block size or is it 64? Is it page or is it not? So there's little bits that are used here to do that. This one is not used. And the miscellaneous bits, I always love that. They're everywhere, right? It's, well, we might need something in the future. So this actual 4 here are kind of a waste. And then, there's protection bits, which if you have 3 bits, you can do 2 to the 3 operations. So whatever protection you want to put on it that way. So different way to look at the same thing, but this is actually 34, right? Yeah. So taking some of that other stuff out of there, but same kind of concept where we've got segment number, the actual the page number, and then the offset to describe that. Now, if you did all the 2 to the whatever sizes in this, you get to see how big everything could be, which this is not getting into very large segments of memory. And then kind of looking at this in its, how does it relate to everything else, knowing that you've got, everything from the descriptor defined here, basically pointing at this, which is pointing at the page frame, and then getting you to the offset of exactly where it is. So that's how these things kind of translate down to their independent pieces of where they point at. So the descriptor points at specific parts of the page table, and then this actual frame would point at the actual page, but again, based on its offset. And another way to kind of look at this whole look-aside buffer idea is that, okay, so let's look at all these segments, and instead of, necessarily just, going out and randomly just finding stuff left and right, let's look at the stuff that's, been sitting right there the whole time. So it's the same look-aside buffer as we've used before. So when we think about how x86 actually worked, and so we did go through many versions of 86, so it was 286, 386, 486, 586, and then they kind of gave up and changed it all into what we have today. But just based on that platform and taking segmentation with paging and how is that done, we kind of look across and we say, when we look at these 16 bits here, we can look at an index, and then we've got a couple different things to identify those, and we'll see next here kind of how those kind of break out. And again, we're looking at different segment sizes. So this is 16 and 32, and here in this whole 32-bit segment, it's really defining a lot more than you'd think of, just not just the address, but you can see all the different components or the different pieces that kind of define out, is this in memory, is it not, and all that. And all these can be used very quickly in different forms of selection to ask questions of it, which might help, for memory allocation, might also help for, identifying, is this something that, from a protection standpoint I shouldn't be doing, or is this read only as an example and I'm trying to write it, but defining all of this in segmentation with paging is something that we're trying to add this to add more efficiency in how we deal with memory and memory allocation. So very simply, this one kind of would go down and it would take that selector, and then based on the descriptor, it would find its base address, add the offset to it, and that would give you your actual address. So it isn't that we're just holding these big tables with all these memory addresses like we put them all up on a chalkboard. It's that we use functions and algorithms to really define where things really are, because a lot of times it's easier just to kind of make it common, and especially when you get into virtual spaces, excuse me, easier to carry around, data that could represent it versus, all the data that would be there. And then finally kind of looking at this, and we'll see a lot of these kind of breakdowns of address components, and keep in mind that, what you're seeing here is 32 bits, but the bits all define kind of everything. And so we could say that if you have 2 to the 10, that's the max size of your directory, 2 to the 10 for pages, 2 to the 12 for offset is the size of memory. So as these different things are identified and used, we're just stripping off the first 10 and identifying this, which points us to the next one. Then we leverage this piece here to then go find that, and then based on its offset, we get to the actual one. So just a different kind of way to go look things up in different tables. And that's it for lecture 3.